the nice introduction. Thank you for giving this seminar, because this is a great opportunity to talk to you about what I'm doing. Because as a fellow here, we may have collaborations, and it's a good opportunity to show you my previous work and my current work and my future prospects. Also, to give you some idea of the tools that I offer in the toolbox of the Institute, and of course, reach out to people that may help me in future steps for this project. So if we look at
you can't hide this in the one.
Sorry. Yeah, thanks. So if we look at the normal galaxies in X-rays, we'll observe many point sources. Most of the sources are going to be very luminous in external galaxies. And we believe that these sources are predominantly X-ray binaries. So there are systems where a compact object accretes matter from a companion star. Now, there are two main classes of X-ray binaries. The first class is low mass X-ray binaries, where the low mass thing goes to the mass of the donor. You have a low mass donor of around 1 solar mass or even less, that when it involves in many hundreds of mega years or even giga years, it expands, it fills its Roche lobe, and then matter overflows from the Roche lobe into the compact object, where an accretion disk forms, which is heated and it emits in X-rays. Another class is high mass X-ray binaries, where we have young stars in young stellar populations, where they have dense stellar winds, and through the stellar winds, they can transfer material to their compact object companion they have. They can also be Roche lobe overflowing, as in the first case, but most of them are stellar wind accreting sources. So the formation of these systems is very interesting. It passes through many stages of single stellar evolution and also binary stellar evolution. So you have the Roche lobe overflow because the star expands. You have a supernova, you form a neutron star, or maybe you form a black hole, and then this system evolves. Even stellar winds play a role because they change the orbital configuration of the system. And there are many physical processes that go all the way here in order to form an X-ray binary. So binary evolution theory models try to predict this behavior to understand the systems. And X-ray binaries, since they are very luminous and we can see them in many galactic environments, offer a great opportunity to understand the binary evolution theory through them. One way to observationally look at the populations of X-ray binaries are luminosity functions. So the number of X-ray binaries you have per star formation rate in a galaxy, for example, for different luminosities here in the left plot. Also, in elliptical galaxies or early type galaxies, since we have all stellar populations, you can look at low mass X-ray binary luminosity functions scaled with the stellar mass. Now, this contains a lot of information about what's happening in the systems, because at different luminosities, you have different types of systems. Now, let's focus in this region above 10 to the 39. This region includes sources from both populations, high mass and low mass X-ray binaries. And why is it interesting? Because the 10 to the 39 L per second is around 10 times higher than the Eddington luminosity for a solar mass black hole or a neutron star, roughly. So in order to have 10 to the 39 Earth per second luminosity, you would need black holes larger than 10 times the solar mass. Now, this is interesting because all previous estimates, all previous studies of black hole masses in stellar populations show that this is roughly the limit. Most of your black holes in X-ray binaries that we observe are up to 10 or 15 solar masses. So this is very interesting. initially people thought that maybe these are AGN, but when they developed better telescopes with high resolution, they saw that these systems, these ULXs can be found in all the way in the spiral arms in a galaxy, like in the picture at the right. Now, there are also some other scenarios that do not include X-ray binaries, like supernova, hyperluminous supernova remnants, or intermediate mass black holes. But all these scenarios cannot explain the number of sources we have. All these scenarios might have some contribution in the ULX populations, but very small. So people believe that possibly we have super-Eddington accretion in these systems. And this was highlighted by the discovery of a pulsar ULX. So they discovered that you can have a ULX in a neutron star accreting object, which means that the system surpassed its Eddington luminosity by a factor of hundreds of times. So the ULXs, just because they are as they are, they can help understand accretion physics in extreme mass transfer rates. In these cases, there are models that predict that when you have super-Eddington accretion, you form a thick disk close to the compact object, and you can have a beamed emission, geometrical beaming, which makes the sources appear more luminous because the Eddington limit we take along the spherical surface, right? Also, we might understand other types of systems that are highly accreting, like intermediate mass black holes, which are very important to understand also supermassive black holes. Intermediate mass black holes are considered to be the seeds of supermassive black holes. As I mentioned before, binary population synthesis can use X-ray binaries to understand, to let's say, constrain its parameters. So trying to match the observations to theory, we will learn a lot about binary physics. And this is important because most of these phases that X-ray binaries pass through are the same phases that gravitational wave sources pass through, compact object mergers, or gamma ray bursts. All the phenomena that are important for X-ray binaries are, let's say, not all, 90% of the phenomena that are important for X-ray binaries are important for all the other interesting class of objects. And there is evidence that ULXs might be more numerous in the early universe. And this poses some questions. Maybe the powerful emission they have in the early universe and the numerous ULX populations is important enough that they are players in heating the universe during the ionization era. So how can we approach these problems and how we can understand ULXs? Now, studies of individual ULXs, like spectral and timing studies, can tell us a lot about accretion physics. However, they cannot tell us about the formation and evolution of the systems. And also, there is the problem that ULXs are very rare, so usually you find them in external galaxies at high distances, so you cannot have observations that resolve accretion properties that efficiently, but still, from individual studies, we have learned a lot about accretion physics. However, to tackle the problem of the formation and evolution of ULXs, we have to do demographic studies of ULXs. So, as I mentioned, old stellar populations, young stellar populations, early universe where we have low metallicity, all these play a role. So by looking at what is the rate of ULXs as a function of the star formation rate, of the stellar mass, or the metallicity in a galaxy, indirectly you get information about their formation and evolution. So previous studies, for example, measured the rate of ULXs per star formation rate. The most recent complete study of demographic study of ULX populations was from Schwartz et al. 2011, which measured 2 ULXs per star formation rate. However, luminosity functions that were created after this study are finding around 4 times less ULXs. In elliptical galaxies, where we have old stellar populations, so we're looking at the degraded history of the galaxy since they're living for hundreds of mega years or giga years. So the scaling should be with the stellar mass instead of the star formation rate. These studies show a rate of around 6 ULXs per 10 to the 12 solar masses that are roughly consistent. And of course, one very important aspect is the scaling of this factor of the ULX per star formation rate, how it depends on the metallicity. So in dwarf galaxies, we found more ULXs. Or in the early universe, we expect to have more ULXs. So this is a very important result from Mapelli 2010. However, as you can see, the scatter is huge because we don't have metallicity measurements for many galaxies, and especially at low metallicity. So all these are local universe studies. So the project that I'm doing here is connected to all my previous steps from my PhD and on. So this is a long project from 2018 to 2024 plus an error term there. So step one in my PhD, I was trying to collect reliable information on ULXs and host galaxies to constrain better the observational data. Then in my postdoc, I joined a team of Tassos Fragos in Geneva University, where we're developing population synthesis code with detailed population synthesis in order to get more reliable mass transfer sequences of binaries. I will talk about this more later. And then here, I will try to combine these two. I will try to use this population synthesis code in order to constrain parameters of binary evolution models using the observational data. So the first step, I had to collect a lot of information about ULXs because ULXs are rare, as we said. And also, you have to take into consideration contamination from foreground and background. These are galaxies at high distances. You cannot reliably say that this source is an X-ray binary, this source is a ULX. It might be a background AGN, it might be an AGN in the same galaxy, it might be anything. So you have to do this statistically when you're talking about hundreds of sources. And since the AGN in a host galaxy might be a ULX imposter, but also bias estimates of star formation rate and stellar masses, as we mentioned before. These estimates are mostly coming from infrared studies, and you might have contamination from AGN. So we need to know which one of these galaxies in our sample are going to be hosting an AGN. So we need a galaxy catalog providing a lot of this information. And this information is not readily available in galaxy catalogs. So the first part of my PhD was to create, along with collaborators, the Heraclean Extragalactic Catalog, or HECATE, which includes 200,000 galaxies in the local universe. This is mostly from Hyperlida, so it's most of the galaxies, maybe 99.9% of the galaxies we know in this redshift area is in the catalog. And we got a lot of information from various catalogs, like photometry, and we measured distances, star formation rates, stellar masses, metallicities, and also nuclear activity classifications. So the galaxy catalog is not something that I'm working on right now, but I'm very happy that students at the University of Crete are right now expanding this catalog. They have even PhDs working with the catalog, and it has been used for educational purposes in Geneva, and of course in science with collaborators. Talk to me if you think that your research can exploit the catalog. And also, these galaxies are up to 200 megaparsecs, which is very high when you're studying X-ray binary populations. But since I was doing most of these steps automatically, I said, why not go further at 200 megaparsecs? And this coincides with the horizon limit for gravitational wave sources of binary neutron stars in LIGO and Virgo. So one case study that we did with the catalog was to see how it can help localizing the sources, gravitational wave sources. So if you have a gravitational wave source, you have from the gravitational wave detector some localization, have some 2D localization and 3D localization using the redshift, and you might have thousands of galaxies in this area. However, when you include the information of the star formation rate, stellar mass, and metallicity of a galaxy, from binary population synthesis models, you know what is the expected rate of these galaxies to be hosting a binary neutron star merger. So you can rank the galaxies. So when you have a detection using the 2D information, you say this is the ranking of the galaxies. I have many possible candidates. Here is the most reliable candidates from this analysis, but the true source of 2017 of the binary neutron star merger is there. When you include the 3D information, you have a better contrast in the ranking. The ranking is shown with colors, so you can go closer to this region. Local universe is clumpy, so if you have the distance, you go better at galaxies that might be in a cluster or something. And when you include the information of the stellar population parameters of the galaxies, then in this case, for example, using HECATE catalog, the first galaxy you select, the higher chance of being the measure, is actually the true that was discovered there. So, of course, this is a side thing. The important thing was to use this catalog for ULXs. So, cross-matching the HECATE catalog with transfer source catalog too, we get tens of thousands of galaxies, tens of thousands of sources in thousands of galaxies. By doing various selection criteria in order to have reliable data, we arrived at a catalog of 600 or more than 600 ULXs in around 600 galaxies in our sample, which is an improvement from previous demographic studies. Now, as I mentioned, we should exclude AGN hosting galaxies because we don't have reliable star formation rate and stellar mass estimates for those. And of course, we have to account for small number statistics because you have one ULX, maybe from your background, you expect 0.7 ULXs. So you cannot say you have 0.3 ULXs in this galaxy, right? You cannot subtract it. You have a Poisson modeling there, which is very important in these small numbers. So the first result was the number of ULXs, the scaling factor of the ULXs with respect to the star formation rate. So in that case, we find half of the ULX per star formation rate in a galaxy. Also, we have a large enough sample to also study the dependence of this rate with the morphological type of the galaxy, because people have observed that irregular galaxies contain more ULXs per star formation rate than large-scale spiral galaxies. So this constraint here is consistent with the X-ray luminosity function studies. However, it's 4 times less than the previous demographic result. Now, having the morphological dependence, you can correct for the biases in a sample. So SMARTS, unfortunately, couldn't have more large-scale galaxies because used a complete sample up to 11 megaparsecs. So the sample contained a lot of irregular galaxies. So if you correct for this factor and some other factors of how you calculate X-ray luminosities, it is consistent. The large sample also helped in order to see the dependence of the number of ULXs, both with star formation rate and stellar mass. This is important because when people try to measure the rate of ULXs, they go to a sample of galaxies that are very high star forming in order to exclude the population that might be coming from old stellar populations, which scales with the mass. So the scaling with the star formation rate and the mass assumes that you have on one hand, a highly star-forming galaxy sample, and on the other hand, an early type galaxy sample. So by doing this, we can have a better relation with both parameters, and we still find some evidence that the scaling factor with stellar mass depends on the morphological type. So in early spiral galaxies, you find that the scaling factor with the stellar mass is important. It's a very confident result, as we see in the second figure here with the orange. So essentially, it's the first time that we see in a large sample that you expect that, but it's the first time that we see that you have to account for the stellar mass of the galaxy when you're trying to, let's say, predict the number of X-ray binaries or ULXs you have in the galaxy. Then if you take this relation, you can also use it as an expectancy of the number of ULXs, the average relation, and then you can plot the excess of ULXs in beams of stellar mass and star formation rate with respect to the expected number. This tells you that the average scaling relation, of course, is created by contributing galaxies all over the star formation rate and stellar mass plane. However, when you do this exercise, you find that you have more ULXs in low mass galaxies, which is kind of known, but here we could quantify it. And this is possibly a metallicity effect. As we've seen from Mapelli and 10, we know that ULXs are more numerous in low metallicity galaxies, and low mass galaxies tend to have lower metallicities as well. So directly looking at the scaling of the excess with metallicity, if we take the sample of Mapelli with orange points, and then we also have some orange lines here which indicate galaxies with no ULXs. So these are zeros, so they cannot be plotted in the log plot here. So if we take a bin statistic method in order to have better statistics, we find the dependence on metallicity. And in our sample with HECATE now, we have these blue points there that extend the relation to higher metallicities. But also there is a small offset there. Now, here I didn't mention in the right figure, we see the mass metallicity relation in galaxies. So low mass galaxies, lower metallicities. All these lines there are different prescriptions for measuring metallicity. What you can notice is that there is a clear trend, but the different metallicity indicators can have offsets of 0.7 dex. This tells you that it's very important to see what you're measuring every time and how you combine these measurements when you're doing a study. So this offset is mostly coming from this thing that unavoidably, if you have observations using various metallicity indicators, you might have some systematics there, and this offset is from that. Now, as we mentioned, we have also constraints of the scaling of ULXs with morphological type, and there's a clear trend. Early spirals have lower ULXs per star formation rate, which still can be a mass effect. Later galaxies are usually dwarf galaxies, low mass galaxies, so they're expected to have higher metallicities. So to test this, we also measured the average metallicity in beams of morphological type in our sample. However, our sample is very small. These points, X points in the morphological type versus metallicity plot are our sample. However, they're too small to get averages. But if you take the parent catalog, HECATE, all these galaxies that we have, you can take an average metallicity, and there is a turnover around SC type galaxies. And this is where we have this large gap in the rate of ULXs, where the rate of ULXs increases significantly. And another thing was the scaling of ULXs with stellar mass. In that case, we did a study as we did with the star formation rate. We took early type galaxies. We also took two morphological types, elliptical and lenticulars. And we have find 15 ULXs per 10 to the 12 solar masses, which is around 2 to 3 times higher than previous estimates of all the studies that all the studies agree on. So that was a very peculiar thing, because elliptical galaxies are considered very tidy, let's say. You don't expect star formation rate activity to change the rates a lot. So we didn't expect to see that. So why do we overestimate the specific ULX frequency? As I mentioned before, we excluded AGN hosting galaxies because we don't trust the stellar population parameters in these galaxies. when we tried to include the AGN hosting L-type galaxies, the rate was agreeing with all these studies and also giving tighter constraint. The difference between ellipticals and radiculars was removed from this. They are very consistent. So why do they look okay when we go to AGN hosting galaxies? First of all, including the AGN hosting galaxies doesn't seem that bad because stellar masses in large galaxy samples are taken from mid-different studies, and the mid-different emission of the AGN usually is very small compared to the rest of the galaxy. Sorry. It's around 10% less. So, but still, why now they agree? AGN hosting galaxies usually are more massive. So when you exclude AGN hosting L-type galaxies, you exclude the most massive galaxies in your sample. So maybe there is a stellar mass distribution thing going on. If we take the sample of ellipticals, radiculars, with or without the AGN hosting galaxies, we find completely different mass distributions. This is the cumulative distribution of the log of the stellar mass of the galaxies. And there is a trend. There is a sequence of how much we overestimate the specific ULX frequency with where is the median of the distribution. So this might seem that there is a stellar mass dependence of the ULX specific frequency. And how can you have this? So galaxies, L-type galaxies, here in the right figure, we see Atlas 3D project result from Addendum et al. 2015, where we see the average star formation histories of L-type galaxies separated in different stellar mass beams. So this red zone there are massive ellipticals. And this is their star formation history. As you can see, the massive ellipticals were formed quickly, very early on in the universe, and now they have quenched the star formation. When you go to lower masses, they're more late in this procedure. So there is still some remaining star forming activity that goes back to some hundreds or maybe 1 giga-year. So if you have ULXs coming from intermediate or low mass stellar populations that are kind of old, then you might see some of these systems in these galaxies. So, and ULXs are predominantly young systems, but still there is a tail. If you take this left figure, this is a simulation of the number of ULXs after a star formation burst as a function of the time after the burst. And this is the number of ULXs, and it's in log plot. Most of the ULXs are young. We're okay with the results for spiral galaxies. However, there is still a tail there. So if you convolve this function with the star formation history of the elliptical based on its stellar mass, then you can estimate what is the number of ULXs you expect to have. So if you do this, you get these 3 points there. This is the stellar mass of a galaxy, of a bin of galaxies, and on the y-axis, the specific ULX frequency. Now, in these are the convolution results. These points here are observational studies. Observational studies measured huge elliptical galaxies. So they look at this part of the plot only, and we have a perfect agreement with the simulations. When we do that with our sample, we separate again the galaxies, we measure the specific ULX frequency, we recover this trend. So even including or not including the AGNs. So by accounting for this effect of the age of the stellar populations of elliptical galaxies, we can recover this. This is the first evidence of an age effect of ULX populations in elliptical galaxies. Of course, this needs more study. How much time do you have?
Well, still have 10.
Okay, so as I mentioned before, ULX might be important as ionizing sources and heating sources of the early universe. So here we have some plots showing normal stellar populations of galaxies, the emission rate of hydrogen ionizing photons or helium-2 ionizing photons as a function of the time after starburst. So this tells you that the stellar population might ionize its interstellar medium, but it depends on the age as well. However, this faint blue line comes from starburst 99, which is a single stellar population synthesis model. However, when you include binary effects there in your populations, like in BPAS from Eldridge, which is this gray zone, you might find that you have more emission and more ionizing emission radiation after some mega years, which means that your stellar populations change because they belong to binaries. You might have a compact object stripping a star from its envelope, and then you have a helium star that has a completely different spectrum. So by accounting detailed stellar evolution and structure when you're modeling populations, you might find interesting results about the ionizing radiation in galaxies. And there is also evidence from that binaries are important in this case, but also X-ray binaries are very important because they're very luminous objects. And they have some soft emission that can ionize the ICM. And we can see that in bubbles around ULXs and the stellar medium. So there is an interesting question whether ULXs can be very important for this process. So here we show in the figure, I show this model that when you have super-Eddington accretion, you might form a thick disk around the compact object, very near to the compact object. You might have beamed emission. The emission is emitted from above. And depending on from the angle that you see a source, you might not see it at all in an X-ray setting. It's completely hidden. So this might seem like an ultra-luminous soft source that might have a very low luminosity in your detection. So this is interesting because you have powerful sources, you have all these ULXs, but maybe there are more out there. So they're more hidden. And if you have a neutron star scenario where you have very high Eddington ratios and very small mass objects and very beamed emission in order to reach the X-ray luminosities that we observe, then you might have a huge population of ULXs that we cannot see. But this population can still ionize ISM. So while X-ray scaling studies, you observe, you measure, you test with binary population synthesis, they might match, but maybe for ISM studies, you need this hidden population. And because you have this thick disk, and you have outflows, wind outflows from the system that creates this funnel, you might have also softer emission that is reprocessed, and you have a soft X-ray spectrum in the ULXs, and soft X-rays and extreme ultraviolet, which is very important for ionization. So let's go faster there. This is a semi-analytic approach where we take the X-ray luminosity function as an observable, and we try to model what are the masses and the mass transfer rates in a population that agrees to the observation. By doing this and modeling the photo field of the wind from the outflows of the ULX and also the disk of the ULX, we can arrive at, this is just the parameters of the systems, we can arrive at results about the helium-2 ionizing photons as a function of the luminosity of the source and also the compact object mass, which we cannot recover. We have to assume we can take 3 indicative values and we compute that. By doing this, we can measure for galaxies in various metallicities, what is the rate of ionizing photons of hydrogen, of helium, of neon, and many emission lines that are important in ISM studies. By doing this, we found that we cannot explain the population of helium-2 emitting galaxies, which is a puzzle that initiated this study. But however, there are some neon-5 emitting galaxies, a small sample, which in that case, ULXs might be very important. We can also take, we also computed the spectra, and we can give it to studies and try also to scale it with metallicity, so people can take this and can put it in cosmological simulations and try to find the properties of IgM heating, for example. And the final part, the binary population synthesis thing is, as I mentioned before, that trying to get to take into account stellar structures, stellar winds, mass transfer, common envelope, all these physical properties in a population, in a stellar population, in order to understand binary projects. This population synthesis code is called POSYDON. It was published a few months. It was accepted actually 1 month ago in Geneva with many collaborators. So this is not exhaustive list. It changes a lot recently, where we model stars from beginning to end. We start with 0-age main sequence stars. We evolve them through the main sequence. We're forming X-ray binaries, all sorts of systems. And we can even go to coalescence of cobalt object stars. This has many applications for gravitational wave mergers. This is the motivation of these studies in this era of gravitational waves, but we can use it also to study X-ray binaries and ULXs. This is from a collaborator, Devina Misra, who defended successfully her PhD 2 days ago, that shows that you can do X-ray binary studies and you can understand what is the fraction of the different types of systems and how it changes when you play with the physics. So this is another plot that tells you what is the number of ULXs in your simulations and how it depends on the different physical prescriptions. Each one of these points, it is a different combination of binary evolution model parameter. So you can understand also the evolution of what happens to a source as it passes through time, what is the progenitor. Here you see this diagram on the right, where you can see the evolution of the system, and you can even have comparison between different physical prescriptions. So the plan here is to do Artife, is to try to understand, to constrain the binary population synthesis models using the observations from the previous results, and also have a better inspection of what is the history of these sources and what we can learn and how they connect to other types of sources, like gravitational wave sources, for example. And for doing this, in order to have realistic galaxy samples, because in binary population synthesis, you start with a star formation history and you can evolve your population. So to do this, I will use illustrious TNG simulations. So I can get thousands of galaxies in a local universe type volume, have their star formation histories for all their evolution, and convolve this with binary population synthesis models in order to estimate the number of ULXs and the luminosity distribution and the types of the sources and all these questions that we looked before. By fitting this data from the local universe, we can constrain binary evolution models. And then we can extrapolate to the high redshift universe, assuming these binary evolution model parameters are correct. So we can have predictions about the X-ray scaling relations and X-ray luminosity functions that will come soon through future X-ray telescopes. One study that we're doing now is to see what we can learn from Athena observations, deep field observations about X-ray binary populations, and how we can, what is the constraining power of these observations with respect to binary population synthesis models. Step 4, no, not enough time for that. Thank you very much. Any questions? There's one in the Zoom. Oh no, this is the link.
She raised her hand. Nanda, can you talk?
Ah, sorry.
So hello. So thanks a lot. Very nice talk. I have several questions, but let's start for. I mean, just make one. So, so my question is: there are many of the ULXs. It's a weird definition in the sense that it's not a physical definition. It's a definition based on luminosity. So my question is, many of the things that you showed, for example, the relation with the metallicity of the galaxy, of the catalog that you did, and all your work, I guess when you say ULX means that whatever you take from the catalog or from the observation, it's a luminosity of above 10 to the 39, assuming the distance of the galaxy. Now, the number in the luminosity function of sources above 10 to the 39 and the one, for example, between 10 to the 38 and 10 to the 39 are very different because you have many more sources at 10 to the 38 rather than the one on 10 to the 39. So how the fact that you cut just by hand a certain luminosity in your definition of your ULXs influence then the conclusion you get, for example, relation with metallicity or ionization or things like this?
Yes, so in order to repeat the question so people can listen from Zoom. So ULXs, as Nanda mentioned, is very correctly defined based on the X-ray luminosity of an object. So it's not a physical definition, just observational. And when I'm trying to do all this analysis, someone might say, what happens when you go to 10 to the 38.5 or 10 to 39.5 per second? So these relations might change, these scalings might change. So yes, this is true, they might change. ULXs, of course, is defined based on the luminosity. So we're not really sure if they're X-ray binaries, if they're accreting sources, if they're super-Eddington sources. We don't know any of these, except for, let's say, 10 sources. So in that case, when I'm doing this study, this comparison with previous demographic results, for example, I'm using the same criteria. I'm trying to do this thing in order to see if there are new constraints, if there is something better that we can do. However, cannot go deeper, cannot characterize the sources. So this is the only tool we have, above 10 to the 39, or sometimes some people use the 2 times 10 to the 39. However, in theoretical studies, like in the analytical study that I did, I used a different definition because I was trying to get, and I was using the X-ray luminosity function, the observed X-ray luminosity function, to get the properties of the systems, go backwards in order to get the estimates of ionizing. So I was using the X-ray luminosity function to bridge the two. In that case, if you go to 10 to the 39, you might have massive black holes that are not super-Eddington. Also, you might lose a lot of neutron stars that are super-Eddington sources, but they do not appear as ULXs because they can still beat super-Eddington at 10 to the 38.5. So when I was doing this, I went above this limit. I went to 2 times 10 to the 39, which is harder to have contamination from from sources that are not super-Eddington accreting. And of course, I was missing some population of neutron stars. So these are caveats that unfortunately we cannot do anything about. But this is an important question. When you're doing the studies, especially in the binary population synthesis technique, I will have to check how this thing depends on the cut that I put on the theoretical simulations, where we have a theoretical X-ray luminosity which does not pass through all the filters that observational studies pass through. So we'll have to use spectra to get bolometric corrections and all these things, but the cut will be higher just exactly because of this problem with ULXs.
Okay, thank you very much.
You're welcome.
Very nice talk. Just I don't know, something basic probably, but why there is this correlation between the metallicity and the number of ULXs?
Yes, so there are various factors. The most important one, or maybe the first that people suspected, is that stellar winds change the orbital parameters of the system. So stellar winds will move energy from the system and the system will widen. So when you widen a system, you make it harder for the compact object to be in the Roche lobe of the companion afterwards. There is also other parameters. For example, the envelope of the mass depends on the metallicity. If you evolve stars at different metallicities, you'll find different envelopes. When you increase the envelope, you might have an early common envelope evolution. So you have one star entering the envelope of the other, so they lose a lot of energy, and there is possibility to merge the two stars. So when you merge them, you don't have a binary anymore. Or maybe you go very close and you turn the thing and you have a very contact system. So all this is a very sensitive function of the stellar structure, which depends on the metallicity. And stellar winds is the common suspect. So it's understood. Actually, it's reproduced by binary population, binary evolution. It's reproduced this trend.
So I have a basic question. Have you looked at how the populations of ULXs evolve with redshift with your current sample?
With the current sample, unfortunately, we cannot. And actually, we cannot isolate ULXs in large distances. Sometimes people can try to go to 100 megaparsec, 200 megaparsec, but then you have the caveat of confusion. So to do that, you need to actually get integrated X-ray luminosities from the galaxies. So you cannot separate them, and you say that based on my population synthesis models or my ULX models, these 100 galaxies would have that many ULXs, so their total luminosity is around that value. So unfortunately, you cannot go to galaxy per galaxy basis, and there are more caveats there. But still, through the simulations, I will try to see the redshift evolution of all these X-ray scaling relations, because from simulations you get everything. And the observations that already exist up to redshift 2 or 3, they're not very tight in order to have constraining power on the models yet. But with future missions, we're going to get even deeper, and we're going to see the redshift evolution of X-ray luminosity of galaxies, of normal galaxies, and indirectly connect with the ULXs.
Thank you for the talk. As you said, so this ULX definition is above LX 10 to the 39, right? That's per second, but there's no upper limit on the effect. Yet you exclude AGN as possible explanation for these ULXs. However, you can have a 10 to 42 F per second ULX, and this would be an AGN, and it is bright for the Eddington accretion. So, and also there are some works that show ULX of more than 10 to 41 X per second, which have kind of a faint optical counterpart around them, like if it were a host galaxy, like a secondary galaxy that has merged with the ULX main galaxy. So, why do you exclude AGN?
Yes. So the question was, I'm excluding AGN And this might have an importance because there is no criterion for the upper luminosity of a ULX. So if you go 10 to the 42, you might exclude some part of the population, or maybe something that appears as AGN. Am I transferring this question correctly? So the interesting thing is that in the observational part of this work, when we did this study, we of course did some cross-check and see what we are missing when we exclude AGN sources, or what we exclude when we cut out central regions in AGN hosting galaxies. So in the catalog, we also provide sources in AGN hosting galaxies, but for those, we excluded some region in the nucleus. Now, by doing this, we found, for example, that the most luminous sources that we had in our sample was 10 to the 41. So the number of ULXs, since we don't expect that a ULX will be more luminous in the nucleus of a galaxy, in the sense of an X-ray binary being more luminous, then by having all these thousands of sources, we knew that either our ULXs above this luminosity limit are going to be so small in number that will not affect the statistics. Of course, you might dilute ULXs because central regions in galaxies are clumped with stars and they still have star formation and you have high stellar density, so you might exclude ULXs by doing this. And this is true. This is a caveat of these demographics. However, it's not a caveat when comparing to other observational studies because they all did that. They had to do this because the contamination from nuclear activity would be very, very high. I don't know if this answers completely.
Yeah, more or less. I meant the fact of ULXs being satellite galaxies hosting nuclei, rather than being X-ray binaries. Yes,
so there could be other galaxies that are in the process of merging. For example, they have even low luminosity AGN, let's say, and interacting with that. In that case, I haven't studied these scenarios, but my guess, in order to look at this and what people believe, would be in the direction that you expect these processes to be more prominent in elliptical galaxies. You have a lot of mergers and recent mergers, and no correlation with star formation rate regions, with spiral arms, for example, in spiral galaxies. So these correlations that were found in early 2000s with spiral arms or with ages of star-forming regions in external galaxies show us that these, most of these ULXs, most, not all, are coming from actively star-forming regions. However, in this study that we did, I also measured the rate of ULXs as a function of the galactocentric distance of the galaxy. And I did that for different morphological types. In elliptical galaxies, there was an upturn at the outskirts of the galaxy. So we had more ULXs when you're going to 1 d25 distance from the center of the galaxy than you would expect. It doesn't drop, it starts to increase. I modeled the background to see if this is background because you also increase the surface there. And it cannot explain. So this could be an evidence of some population of ULXs that are in merging galaxies around mostly massive ellipticals. Because I also checked with bibliography and I found that some of these galaxies have been studied for their mergers. So there might be something there. Whether it is normal X-ray binary populations from the merged galaxy, smaller dwarf galaxy with low metallicity, low mass galaxy that is glooming with X-ray binaries, or whether it's a low luminosity AGN in this galaxy, I don't know. I don't know if someone has looked at this in a demographic study, in a large sample, to answer if it's very likely.
Okay, concludes the session, so probably go to the passion. Thanks a lot.
Thank you very much.